Everyone enjoyed the poster session last evening. We've got another fun-filled day ahead today with some great talks, hikes to the green room, all kinds of fun things. Catherine will tell you a little bit more about those things. This morning, it's my very great pleasure to introduce our keynote speaker, Fernando Perez. He's a staff scientist at Lawrence Berkeley National Laboratory, founding investigator of the Berkeley Institute for Data Science. He has a PhD in particle physics from University of Colorado at Boulder, and as a grad student in 2001, he created the IPython product and continues to lead Project Jupyter today. So those of you who were in sessions yesterday, at least the ones I was in, saw an awful lot of mention of Jupyter and demonstrations and tutorials and things like that. So here we get to hear from the very creator of that. Fernando regularly lectures about scientific computing and data science, and he's the recipient of the 2012 award for the advancement of free software from the Free Software Foundation. So let's welcome Fernando.
Thanks, folks, for being here, and first of all to Nancy, Shreyas, Catherine, and the rest of the organizing committee for inviting me to be here. Speaking to you, it's been a really fun experience since yesterday. First, by California state law, anything good that I say about these companies might be biased in some way since they've supported my work and the work on this project. But I sort of want to frame the context of this project from this very old quote that many of you may be familiar with, which is from a numerical analysis textbook from Hamming in '62. And if you think about Hamming worrying about people just getting junk out of computers and not thinking about what they were doing back in the '60s, imagine we all have more computing power in our pockets today than Hamming could have ever imagined back in 1962. And so this is really a concern. And now it's not just compute, we have data. We've all seen slides like this about kind of the flood of data in every discipline. I don't need to belabor this point. The question is, with all that data and all that compute power, we still have one of these, and it's not getting any bigger, right? The amount of brain that we have isn't getting any bigger. We're all living actually to be older, therefore we're struggling even more so with that. Our computers might have been things like this. Our laptops and individual workstations where we play with our code and data, they can be big toys, like our lovely Corey down at NERSC, at LBL. And what we've tried to build with the tools in IPython and Jupyter is to be the bridge between our limited puny brains that are trying to make sense of the world and these silicon toys that we keep building and keep getting bigger. And so IPython was born out of procrastinating a little bit of hopefully productive procrastination back in 2001, trying to bring some sanity into my workflow for the analysis of simulations in QCD. It's interesting that actually now when I walk into my office at NERSC and I see the screen that shows the top jobs consuming CPU cycles on Corey, Dot Toussaint's QCD codes are regularly still the #1 or the #2 job there, which is the codes that I was analyzing back in 2001. But it was really born as a very simple environment to let me look at code, run some code, play with ideas, look at my data, look at my file system, basically have kind of something at my fingertips that would help me think about what I was doing with computation and data. But today this is a big project, and everything I'm going to show you, the credit goes to these people. There are actually 2 of these people in the room. Shreyas Cholia, who's one of the organizers of the event, who's my colleague at LBL, and Carol Willing, who's one of our engineers in the project, and who lives and works here in San Diego. These people are really what makes all of this possible. It's a combination of industry, of academia, of government research, of open source contributors. My co-PI on the project, Brian Granger, is faculty in physics just up the road at Cal Poly in San Luis Obispo. And it really is a team effort, not only from all these people, but from a very broad open source community. And we try to kind of be a project that is open and a good bridge between all of these environments with sometimes competing needs. We're thankful for the funding that we've received, and as you'll see, it's a combination of private foundations and companies, and recently, actually, some DOE funding that I'll talk a little bit more about with Shreyas. But over the years, what happened was we started basically abstracting over that very simple idea of typing code out of command line, looking at the results, popping up a plot, and we turned that simple interaction between you as a human and the computational resource into a protocol. We basically turned the read eval print loop into a well-defined network protocol where something on one end could execute code and something at the other end would receive the results of that execution, would display them, would present them, would also take your input actions. And with that, the first thing we built was something that was, in 2010, a graphical interface that looked kind of like a terminal, but actually wasn't a terminal. It was a Qt application that could have syntax highlighting, multi-line editing, inline figures, the kinds of things you can't do in a classic kind of terminal emulator. It turns out now terminal emulators are starting to do all this stuff, but back in 2010 they didn't. But that was a stepping stone towards what became the Jupyter Notebook, which is, I probably don't need to explain it too much because I've seen mention of it, but for the sake of completeness, it's an environment that accesses the same kind of computation, but now through a web client, and it actually stores that in a document. So it's not just an ephemeral console, it's a document. The first approximation, I like to describe it as Google Docs with a brain, because you have a document, you can type code, you can type text, you can format the text, you can type mathematics, but you can also type code. That code will execute and will have results. You can even have interactive controls in there. And so pretty much anything that a web browser can display, you can put in there: audio, video, JavaScript, etc. And these are documents that can then be shared. They can back your research in a reproducible manner. They can be used for teaching, etc. So by designing the system in this way with these decoupled abstractions, what we were able to do is build a project that not only had Python at its core, but also had support for other languages, because what executes the code in the back could be anything. And so Julia is a language that I'm very interested in for numerical computing, and we worked with the Julia team to build what we call a kernel for Jupyter in the back. R is obviously a language that is very important in data science. And so these three are the three languages that inspired the name: Julia, Python, R. It's not an acronym, but it's kind of an inspiration coming from the open languages of data science. But once you have a protocol, you can implement that protocol in any language. And today there's roughly 75 kernels that implement this protocol for a huge variety of languages of various degrees of completeness and quality. Some of these are production quality tools, others are kind of afternoon toy projects. And with these ideas, I think we can show that we can bring to life a stand on the question of what computational research should be that has been advocated for by folks like David Donahoe back 20 years ago. So this is a quote that I think is a very important quote, because it frames the problem in a really clear way. And David Donahoe who's a statistician at Stanford, well-known statistician at Stanford, who does a lot of work in harmonic analysis and numerical algorithms, said this over 20 years ago. And I would like to argue that now we have kind of existing proofs with these tools that this can be done. This is an example of a paper that came out in Nature in 2014 about head and neck cancer. I'm not qualified to judge its scientific merit, but for the sake of argument, let's assume that it was properly reviewed by the fine editors at Nature. But the point is, the authors actually left the paper as the advertisement. And then there's a GitHub repository that has not one, but 20 notebooks, where every step, every figure, every paper, every result, every number that is quoted in the paper is actually produced there. And you can clone the repo and run it yourself and build on that research. So, and this idea now has been turned into a one-click action for sharing. So there's a project called Binder that was started by Jeremy Freeman, who's a neuroscientist at Janelia Farm, Howard Hughes medical investigator. And what Binder does is it gives you a single text box for you to type the name of your GitHub repository. And if you have prepared that repo with a collection of Jupyter notebooks and the dependencies of the libraries and tools that you need, and you can do that in a variety of ways, you click submit, and he automatically will build you a Docker container that has all of that ready to go and actually give you a URL to execute it, so that you can run that off his pocket, off his grant money on Google Compute Engine. And his lab keeps basically a cluster of nodes on GCE available for this. It's a free service, so it's best effort, but it still demonstrates the idea that this is completely possible, and it's not a fiction, it's not an idea, it just works already. And to prove that it works, this is, and I don't have time to do a demo of this, but the LIGO is the collaboration that did the detection of gravitational waves that was in the news a lot earlier this year. The LIGO collaboration now releases all of their analysis in the form of Jupyter notebooks, and after we show them that these could be binderified. Now on the official Open Science Center for LIGO, you will find links for every new release to a binder, so that you can literally click on it and re-execute the LIGO gravitational wave detection analysis yourself without ever installing or downloading absolutely anything. And they actually provide two links, an Azure binder one, and then one to run on Azure, because Microsoft is now also providing the same kind of service. So you can choose which one you want to run in, which means with your Azure account, you can use it even if binder is busy. And this is being used really to try to show that we can change the scientific culture. A couple of years ago, we did a little bit of work with the editors at Nature, who were writing pieces about open science and sharing how to better share computational research. And what we did was we put up on the Nature website a hosted version of a notebook that had basic ideas in scientific data analysis. Now, this was not a new paper. This was not new results. It was just a demo, but it was a scientifically realistic demo using data from the Hubble Space Telescope to show you how to do basically simple image processing that would lead to detection, object detection for what could be potentially galaxy clusters. The point is, this demo set up there showed that the notion of making available to the public through a journal the results of scientific research for the public to actually experiment with while they run the analysis and then move on from there is actually a reality. This is not an idea. This was done in November 2014. And so those ideas are the tools that we've built for you to interact with your code. But science and education are collaborative efforts, and so we've taken one step back and built actually a platform for this to be shared with others. So in addition to the Jupyter machinery for you to interact with the code, Jupyter Hub is a project coming out of our effort that now allows organizations to deploy these systems for their users. And it was designed because once you start getting into the realm of larger deployments, then everybody really is their own special snowflake. As we know, every supercomputing center, every HPC deployment, somebody's using the cloud, somebody's using their cluster, somebody's using the cluster is just a beefy desktop under somebody's desk. And all of those things are valid because they're different use cases. And so what we did was we made authentication be completely pluggable so that you can either have local accounts or you can say connect to your campus authentication system. I'm hoping that we're going to have a GlobalSoft one pretty soon. You may be running live on the bare metal, or you may be saying, oh, all of this is being deployed via containers that define different environments for our users. And so with these tools now, we have an environment that I know some of you are actually already deploying that allows you to then manage other services and integrate them with the Jupyter Hub APIs so that you can, for example, have a notebook sharing viewer that actually runs inside of your organization and is protected by the same authentication credentials and has access to the same code and data. So we've started to define services APIs for this to be built precisely kind of in the spirit of what your community has been doing, and I've been trying to learn quite a bit about the use cases and kind of the tools in the space that have been presented. With this kind of machinery, for example, at UC Berkeley, based on the work of a grad student who was faced with the task of TAing for a big course that formerly had been taught with MATLAB. She was porting it to Python, but she didn't want to manage 200 students emailing scripts or putting zip files of scripts in the campus course management system. Jess Hamrick set up a cloud deployment of this with nodes on Rackspace to run a course, and now UC Berkeley has adopted that for the new Foundations of Data Science curriculum, which is an open textbook. It's available on GitHub. You can go to inferentialthinking.com and see the textbook and play with it. But if you open the textbook as you read it, you'll find these blue buttons that say Interact. If you click on those buttons, if you have a Berkeley ID, it will ask for your Berkeley credentials, and you'll be automatically logged into a live version of the textbook with all the code and data and dependencies already available. And so this is how now students at Berkeley have access to these tools, where campus now is deploying it. There's other deployments. I just learned at the hotel that Clemson University here is using it as well, Cal Poly and a number of other institutions. I want to highlight two from folks who I know are here. At NERSC, Shreyas and his team have built a deployment of Jupyter Hub on the NERSC supercomputing machinery, and he's going to give a talk about that. And I know that Andrea Zonka here and his team have also done similar things here at SDSC. We also have a collaboration with folks from UCSD. Larry Smar and John Graham and their team. Larry is the PI for the Pacific Research Platform Project, which is a project to integrate the universities in the West Coast and research centers in the West Coast with high-speed networking and connect it to the compute resources across the West Coast. And the definition of West Coast actually reaches, of Pacific reaches Wyoming, so it's an extended Pacific. But okay, I guess Wyoming has always wanted beaches, so now they have a beach. And Larry and John actually loaned us a node that is basically a beefy CPU GPU hybrid node that we've put at Berkeley. And in collaboration with folks from the Berkeley Research Computing Team and LBL, this is providing now basically a bridge system that is neither your laptop nor a full-blown HPC environment in batch mode, but actually basically a live interactive Jupyter Hub with lots of data, high-speed access, and Andrea configured it to actually have deployment on Comet, so that you can basically, we're trying to understand what is it going to look like to make a smooth transition between what fits on a laptop or a local machine and what should be running on a very large resource, and what are the interfaces, what are the work modes, what are the data access modes that should be deployed for something like that. These are just a couple of examples. There's a few others in the European Union. There's a mathematics, basically virtual mathematics environment project that has a piece of it using Jupyter called Open Dreamkit. Here at UCSD, Jill Messeroff's project, which began back when she was at the Broad Institute, called Gene Pattern Notebook, is using this effectively as infrastructure. The K-Base project at DOE, which is a large and ambitious project at DOE for providing access to biological data and computational resources, also uses basically a customized version. This is a Jupyter Notebook embedded within K-Base's own user interface, data access tools and computational tools. And it's also a project that has been widely adopted by industry. I already mentioned that Microsoft hosts Jupyter on Azure, but Google has its own version called Cloud Data Lab. IBM has one called the Data Scientist Workbench. Continuum Analytics has its own cloud, and there are other companies that offer basically computational infrastructure tied to their own sort of special sauce in the cloud with these resources. But as I said, it's important to understand that we've really paid a lot of attention to making this architecture as modular as we possibly can, so that other things can be built with it. So this is an example. The Interact project is an example of a completely different client that uses the same exact protocols, accesses the same exact file formats on disk and the same notebooks, but now it's a native local desktop application. So you have more flexibility with key bindings. You can define a different security model. You're not going through the web. In some cases, the web remote access is exactly what you want. For example, if you're deploying to a lot of remote users, if you're deploying to a bunch of students and you don't want to have to do effectively IT support for 3,000 students at the beginning of the semester. But on the other hand, if you're in a very well-controlled environment with complete control over deployment, maybe desktop applications are what you want. And so Interact uses the same architecture, but it's a completely independent implementation of these ideas. Now, as it turns out, as I said, what matters is the underlying computation. Sometimes you don't need a notebook. Sometimes what you need is access to the compute resources, but you want to expose them via a different interface altogether that still uses HTTP, but is not a web browser. HTTP is a protocol that, yes, it's what web browsers use, but it is a protocol that can be used in many other ways. Everybody who has ever written or used a REST service has made effectively use of HTTP as a non-HTML, non-display-oriented tool. And so the Kernel Gateway project is a specification and a set of tools to access Jupyter kernels, and it speaks their protocols and translate that in a simplified way into a web service that you can then access with whatever tool is appropriate, basically for the kind of content you're transporting. Another example of a different use case of these ideas is to say, well, I've built a notebook and I have a bunch of code and data that it accesses, but I actually want to expose these computations to someone else who isn't going to be looking at all the code. All I need them to see is some information about it and some controls that execute code when they access those controls, but I don't want to let them see all of the details because they're relevant to their use case. So this is effectively building a dashboard, but you don't want to have to basically rewrite everything every time you're going to deploy it. So with a lot of work put in by Peter Parente and folks at IBM, we now have a specification to basically allow you to take a notebook and by using the metadata that the file format of the notebook carries, define what it should look like and how it should be viewed and what information it should present to a user that is accessing it from a different perspective. But if that person says, well, I actually need this other bit of analysis that wasn't there, you don't have to do a huge rewrite, redeploy cycle. It's just a notebook. Just go back to it the other way, basically open it in full, make a couple changes, close it back, let them see it again, and you're good to go. We have a new project that I wanted to highlight when I mentioned that we have DOE funding. Shreyas and I recently received a DOE internal LDRD grant for about a year to try to ask the question of how to bring human-in-the-loop, highly interactive capabilities in the context of very large HPC workflows that typically run offline in batch mode. A motivating example that we started from was the Palomar Transient Factory analysis pipeline, where they had to run large-scale batch mode analyses of every night of data coming in from transit events. And for example, they had an optimization that that they needed to do to bring the runtime of a particular piece of the analysis from about 40 minutes to a couple of minutes. But for them, the bottleneck in this process that took a long time was the latency of the development cycle, precisely because everything was set up for big HPC mode. Every small iteration you made was via instrumented logs in the database in batch mode, and you had to wait a day or two for the results. How do we bring human interactivity in this context? There's a lot of other projects that have similar needs. And so we have some research questions here that I think are still open and that we don't know the answer to. And we're going to be hiring. So if anyone here is interested, is looking for a postdoc opportunity, or has a student or a postdoc looking for an interesting and fun project to work on, please talk to Shreyas or I and come our way. I want to talk a little bit about where we're going next. So what we call the Jupyter Notebook, which is this thing that I mentioned that has code, has data, results, etc., is actually a misnomer, because when you type Jupyter Notebook, what you actually have is also a file manager. You also can open a terminal emulator. Turns out you can open a text editor. You actually have a process manager that tells you what is running. You also have a cluster manager. So it isn't really a notebook. That term really is a misnomer. What we built is really, we've been adding the tools that we know are needed for these problems, and these are things that have been added by kind of organic necessity, but they've been kind of added in a very Frankenstein manner, and you can see the fixed staples everywhere. So what we did was we tried to kind of deconstruct this, disassemble it, and ask what are the basic building blocks that we need, and reassemble them now in a very, very modular architecture that rather than showing you lots of screenshots, I'm actually going to do the something stupid. But first of all, I want to say that this has been an example of a very, very intense collaboration between the project and folks at Bloomberg Tech and Continuum Analytics, who have been doing a huge amount of the implementation work. And it's kind of an example of how these open source projects can bridge questions in academic research with industry concerns. Before I do the stupid thing, I also want to flag that I can't give too many details yet, because these decisions were, many of them were made just a couple days ago. But if you're interested in participating and engaging with our community, we are going to be running a conference next year in New York City, and the dates are probably settled. Just about nothing else is settled yet, but those dates are settled, and we hope many of you will participate. But now, in terms of stupidity, the thing that you should never do, which is deliver a keynote by doing a live demo. So first, I want to thank the people who wrote a lot of the material that I'll be demoing, but I'll take the blame for the screw-ups. Because what I want to show you is exactly what it is that we're building. What is this JupyterLab thing that we're building? Is I think it will be exactly the kind of tools that will be of appeal to many in the room. This is, by the way, very, very alpha. So we call it an extremely alpha preview, and we mean that. I would not put this in front of end users quite yet, but I think it is time for a technical crowd like this one, which has a lot of development activity, to begin looking into it. So what we've done is we basically brought all of these tools into a plugin system, where now, yes, you can open a new notebook and you can say, I want to have a new notebook here, and you have a new notebook, and it's exactly the same thing that we've always had. You can type You can make plots, etc. So nothing has changed. The file format on disk is the same, which means that if something doesn't work here, you can just save it, close it, and reopen it with the classic notebook, and you're good to go, because we didn't want to break that part. The underlying protocols are the same. But now this is an application where you can, where you have a file manager, you have the process manager, you have the tools. These things can be organized in a variety of ways. You can say, now I actually do need a terminal here. and I want to monitor what I'm doing while I run. I don't have htop on this guy. I want to monitor what I'm doing, and all of these things are plugins. So literally, if you look at the startup file for this, rather than being a gigantic application, it's just a list that says load notebook, load menus, load help, load terminal, load text editor, etc. And which means you can build your own as well. All right. And so for a very, very quick demo of what IPython and the notebook can do for scientific audiences, one thing that is interesting to be aware of is that you're not only can you have kernels for many languages, you can actually bring through IPython all of that machinery into one space. So this is an example of running Julia code inside of the IPython kernel using Julia to call then matplotlib, and then finishing annotation of a matplotlib plot that you created in Julia back via the Python APIs, all in the same process. And then afterwards, you can pull in some R, and so you can continue doing your analysis in R in the same process with the same data. You can bring lower level C code that gets linked automatically into your code, and you can even have scripting Fortran. So this is an example of saying, oh, I want to write a function in Fortran. And make a change to it. And now Fortran is a scripting language. So for those of you who still need Fortran because it still has valid use cases, there you have it. Now, with this architecture, as I mentioned, you can have interactive controls. So one thing that in data analysis and scientific computing is often important is to do things like parameter exploration, looking at model questions, but scientists are not GUI programmers, and we shouldn't become GUI developers. So one thing that we've done is we've made it very easy to say, well, if I have a function that can say change the RGB parameters of an image or do the convolution of an image with a simple Boring kernel, by simply saying, oops, what happened here? Oh, Apple being useful. Thank you, Apple. By simply asking this function edit image to be interacted with, and saying I want to interact with this particular image, and I want controls over these parameters. Now automatically we can generate a small set of interactive controls for you to modify those things. So this is the kind of code that a scientist is capable of writing. I can say I need to interact with my model with menus and sliders over these 5 parameters. You're not going to ask a scientist to go and develop a GUI. Normally when that happens in your lab, basically it's kind of stop the presses for 6 months until they come back for air. And then you realize that you missed one thing. But this idea of basically very quickly on the fly while you're doing your work, getting just a little bit of graphical usage is very useful. And now what I want to show is precisely the value of having this kind of architecture that we have in JupyterLab, is that all of these things, as I said, are speaking using one protocol. So now I was able to grab this output, put it there, park it next to it, because all of these things are connected by the underlying APIs that use the Jupyter protocols to send and receive data. They're still connected to the same kernels. And now with this architecture, it's not just notebooks, as I said. So this is an example of saying, I don't want a notebook, I just want to edit my file, in this case in Markdown. I can edit this Markdown file, I can add math, and so I say x plus gamma is nice, right? And here it renders it automatically, so I have a live preview. But I can also say, you know what, I do want Markdown, but I actually want Markdown with a little bit of code. So I want to say, here in my Markdown file, I actually want some code execution. So we've attached the kernel to the text editor that is rendering. And so now instead of a notebook, you have a plain text file that can be rendered and converted to other formats, but which can still be connected to a kernel that you specified, and where you can still send code execution to it. Now, you can say, I have a custom data type. For example, I have data in JSON that I want to look at, but it turns out that looking at JSON data like this is kind of miserable. This is an example of museums in DC. Well, you can tell the system that you want to look at that as a map, and this is a much more interesting and valuable way of looking at that kind of data, right? than looking at a text editor. So you can provide plugins that use this architecture to now access the kinds of data sources that are available in your remote systems. And since often we do have a lot of data in these big remote systems, this is a demo of a system called Dask. Who here has heard of Dask beyond Shreyas? Okay, good. Quite a few of you. And Ian, who's here and who's part of this community at Continuum, this is a demo that was prepared by Continuum by Matt Rockland and Luke Canavan at Continuum. And what it's doing is they set up for me an 5-node, 8 cores per node, so 40-core node, 40-core cluster that loaded data from New York City taxi rides. So there's about 150 million records of New York City traffic data, taxi ride data, I'm sorry. And so you have information like the number of passengers, the distance of the trip, the pickup and drop-off locations, etc. And you want to ask some questions about that data. So, for example, to try to find. So here I'm actually running sending to the cluster a job to do an aggregate analysis to try to understand how people tip. And what's happening here is Dask has created a lot of tasks, and these are plugins that use the same architecture to now show you as the jobs are progressing. There's about 240 task runners total active in the cluster, and this was dynamically showing exactly how the task, who was doing what in real time, what tasks were active using the same protocols until we see the data on how much people tip as a function of the time of day. Now, keep in mind, I double checked with Matt, and indeed, the tips hover between 22% and almost 40%, which seems high. This is because this is data where this is only looking at the trips where there was a tip. So it's biased. And one interesting question is, that still seems high. This is the mean, not the median tip. Computing a distributed median is a tricky proposition. This is a mean, and so you can ask a question about basically robust statistics and what are the drunk Wall Street traders who are tipping 400% at 4 in the morning that are driving that data. But the point is, this is an architecture where now we have an environment where from here, not only do we do our normal analysis, but we're now actually controlling a cluster, getting real-time output from it, getting monitoring information, and all of these things have been done precisely using this modular system where others are building things. So what we're really excited about is not so much the tools we will provide, which will be the basic ones from the core system, but rather what will the community be able to do and be interested in building with this system. And to try to keep things on time, I think I will stop here. The demo did work, which was not a given. It had crashed about 2 minutes before. And thank you very much for your attention. I think I have time for a couple of questions. Am I managing questions, or? I think I saw the first one back there, and we'll continue here, and I'll try to work my way. It's Interact, spelled oh, come on. What's that? Oh, GitHub. I can't type with my glass. There we go. It's Interact, but spelled only with an N.
And did you say that the new JupyterLab will be able to combine data and you can work with it in Fortran or MATLAB?
That's already true. That's already true, actually. That little demo I wrote years ago. That has been true that's part of the IPython kernel itself. So the IPython kernel, so there's many kernels for Jupyter, and one is the one that runs Python code, which is the old IPython system. It has what we call magics, which are commands that allow it to do things potentially with non-Python syntax. And so we wrote magics, I mean, by we, I mean the community, to access things like MATLAB, R, Fortran, Python, and other systems. And that has existed for a while. So if you install the R support, you can type R code in an IPython notebook. If you install the Octave support, you can type Octave code. That you don't need to wait for JupyterLab for that. That already has worked for years, since about 2011. I think I saw one here and one back there, and then there. Yes.
File route.
Yeah.
Stuff like that. There's kind of a history where it's a project environment, the kernel is running somewhere where you can put the file system in your terminal. But when you're operating in the cloud or you're trying to deal with other services, how difficult would it be to abstract that, such as the file system is coming from, say, a REST API or an object store, to make it still painless for the user to find and identify their files, operate them in memory, and then get the results stored back?
So I'm going to answer that question with at 2 levels. So the first level is the notebooks themselves, where the main files are stored. That is already completely pluggable, and it's abstracted over an API that we call the Contents Manager API. And for example, Quantopian has written a Content Manager API that runs on top of Postgres instead. Keybase has a Mongo store. We have one that runs on Google Drive. So that has already been done for the main notebooks. Now, for the second one, I would defer to the kind of things that Matt Turk was saying yesterday in his talk, which is thinking of, because at that point, since the kernel is the one running, at that level, things are going to expect something that vaguely looks like open, right? And there's a lot of tools that are going to expect that, but tools like Fuse can present data, and this is exactly the point that Matt was making yesterday, is exposing data sources in a way that looks enough like the file system API, that legacy tools and standard programming language constructs will still feel at home and will operate. And so I think between those two can probably cobble together decent solutions. I think I was trying to move this way, and we'll go back this way. Yes, you, sir, had one first, and then we'll go here. Yes.
When I look at what you presented, I'm missing very focused on the practice.
Yes.
Anything that I've ever done in my life in my science and part of it has required a wide dynamic range of computing that goes all the way from the interactive as the last step, but deep down into massive fast processing.
Yes.
Do you have anything already done, or are you thinking about integrating these time scales? Because fundamentally, right,
yes. Absolutely. That is exactly the challenge and the problem that we're tackling with this new project, Shreyas and I, and we'd love to talk. We've already we're thinking about setting up a call in the next few weeks with Ilkay from here, from SDSC, and others, precisely because there's a lot of people who are beginning to ask that question of really, really spanning that. I think up until now, those two worlds have been very much separated, right? The supercomputer, the HPC facilities optimized for the flatness of the performance curve and the flop consumption, and the interactivity is typically small to medium-sized tools. But now, I mean, when I showed that Dask analysis, it had a very interactive feel. There was a lot of real-time data, but it was running a big job, and that could have been running on a much bigger cluster if you really were in production. So we're beginning to have the tools to go there. I'm not going to claim that we have the answers. Some of the ideas that we have, we should discuss probably offline because it'll take too much time, but we're trying to go there. There was someone here, and I think there was a question back there.
Is there talk with, and maybe this is a half of one question for Nancy as well, is there talk of trying to get a Jupyter based on something like Comet as part of like a gateway?
So you should talk to Andrea, because and the Jupyter Hub Fiona instance that Larry and John Graham sent us is already configured that way. So when you log into those nodes, there's already a Comet launcher already. But you should talk to your local team about that. And Shreyas will talk also about similar things at NERSC. I think, and stop me when we run out of time.
How are you building the API for debugging and trying to track what's going on in GPT?
That's a really, really good question. We haven't done a lot on that. We've had some very, very embryonic conversations with folks at Microsoft from the Visual Studio team. They have put a lot of thought into remote debugging protocols. The kinds of things that I was showing in that Dask demo provide some real-time information that could be useful, but there's a lot more that we should do and that we haven't done. Up until now, the debugging part, we have early bits and pieces, but it's something that we know is necessary. There are people kind of interested, but as you see, we're already tackling a lot of questions. So we're not going to solve every problem. We'd love to have partners on that if you're interested. I think I've been ignoring someone. Let me get back to you. I think you had your hand up. Please.
Yes. Now the JupyterLab is more like Eclipse in a kind of performance.
Yes.
Marketplace plugin development.
Yes. So it's getting started. These APIs. This is why I'm showing it to a crowd like this one, because those APIs are just evolving, and so you should play with them. You should test them. We're sort of having a little bit of convergent evolution, I would say, with the Eclipse and their ilk are coming at these questions from the very much software engineering side. We're coming at it squarely from the interactive side. We are about scientists thinking about their data and computation, but evidently there's overlap, right? Obviously, we recognize those similarities, and the reason why we want people playing with this, at least developers, is so they can tell us what's missing in the APIs. They're getting to the point where they're usable. As you can see, the demos don't. I mean, they work, but they're not really cast in stone yet. So there's time to tell us, what have we missed? What do you want? What are we not doing? No, not yet. I mean, there isn't, but obviously there will be. I mean, I guess the marketplace will probably be GitHub, but yes, that will happen. But first, we want to make sure that we get the APIs right. Rob, I think you had one, and let me come back to you since you already had asked the question. Yeah. If you look at my working notes for the meeting that I have starting on Monday at Cal Poly, those two things are at the top of my notes. We have our all-hands dev meeting next week. Pieces of that are already actually in our grand deliverables, so I have a gun to my head pointed by my funders to address that problem. And the question of unit testing and whatnot has been coming up really, really hard from our reproducible research working group at BIDS in the last few weeks. And so Carol is nodding at me, and she can keep me honest and make sure that I don't ignore what you just said and what Philip Stark has been saying at Berkeley and whatnot. So yes, extremely high on the list, and hopefully next week we'll have a concrete plan on what to do on that. And I've been keeping you in wait.
Security. I mean, what you're showing is really interesting.
Yeah.
And I like to know what security concerns as a user we should be careful of.
Well, I've heard that the internet is a really nice place, and so there's. What do you mean security? No, of course, no. It's crazy. We have what we've done is we've weaponized JavaScript, right? This is weapons grade JavaScript connected in the browser, connected directly with APIs that hook all the way back to remote resources with arbitrary code execution, and that's the point, right? So yes, we are crazy, and it is insane. We have a private security mailing list. Anyone who's interested in security and an expert in security, please let me know. We can add you to the security mailing list. We've already released CVEs. We found JavaScript vulnerabilities that do allow for remote code execution. The IBM security teams have done a lot of analysis of the platform, and we've changed things because of that. I'm sure we will keep on finding them. The only thing I can say about security is we are certainly not experts, but we acknowledge the severity of what we're doing, and we invite experts in security to join us. And in that security mailing list, there are quite a few fairly knowledgeable people, but I'm happy to have anyone else join. We have private shadow copies of the repos where we do pull requests and completely open code review of the vulnerabilities, but in private repos, and the commit logs are sanitized so that when we push into the public, we keep it as basically, we give some wiggle room for people to update before all the details are visible, but the actual pull request discussion happens in private repos fully kind of in an open manner. So we keep on learning on best practices in this topic. So anyone here from this community who's an expert and interested, let me know and we'll add you to the list. Yes, Nancy will stop me.
That's going to have some impact on the way data moves.
You mean WebSockets? Yeah, this is all WebSockets. Yeah, so the way the protocol is structured, the low-level protocol between kernels that speak to kernels is JSON data traveling over 0MQ connections, and there's a very specific connection pattern that we present so that you can have both direct execution and listeners on broadcast. So we have both request reply and POP/SUB sockets for the different kinds of data. But that 0MQ traffic is translated by a proxy into WebSockets. And the actual packets basically go unmodified because there's pretty much a one-to-one mapping between the patterns that WebSockets expose and what 0MQ exposes. And that's what the role of the kernel, if you want a notebook server, the notebook server does that. But if you don't want notebooks, the kernel gateway is basically the low-level abstraction that does that proxying between JSON over 0MQ and WebSockets. And the reason we chose that is because it allows pretty much any programming language that has a JSON encoding library, that these days is just about anything, and 0MQ bindings can do it. And it turns out 0MQ is a very, very compact C++ library with almost no dependencies. And so lots and lots of languages have 0MQ bindings.
I think with that.
Thank you very much, and thanks again for the invitation.